Introduction. In this lab, we are exploring one of the most fundamental interactions in electromagnetism, the magnetic force on a current-carrying wire. When an electric current flows through a wire that's placed inside a magnetic field, the wire experiences a force known as the magnetic force, which depends on several factors: the strength of the current, I, the length of the wire, L, the strength of the magnetic field, B, and the angle between the current and the magnetic field, theta. This relationship is mathematically expressed as Fm equals ILXB, or in scalar form as Fm equals ILB sin theta. In our experiment, the angle between the current and the magnetic field is kept constant at 90 degrees, meaning sin theta equals zena. This simplifies the relationship to a direct proportion between the force and the current. Because of this, if we plot the measured magnetic force against the current, the result should be a straight line, where the slope corresponds to the product LXB. Using that slope and knowing the length of the wire, we can calculate the magnitude of the magnetic field produced by the magnets. The main goal of this lab is to experimentally determine the magnetic field strength by measuring the change in magnetic force as we vary the electric current through the wire. After finding this value, we will design a follow-up experiment using our calculated B field as a theoretical reference. By comparing our predicted magnetic force to our measured value, we can determine the accuracy and percent error of our experimental setup. An important concept related to this lab is the right-hand rule, which helps us determine the direction of the magnetic force. According to the right-hand rule, if you point your thumb in the direction of the current, 1, and your fingers in the direction of the magnetic field, B, your palm will point in the direction of the resulting magnetic force, Fm. This simple but powerful rule helps visualize how electricity and magnetism interact to produce motion, the same principle used in electric motors. Overall, this experiment not only demonstrates the relationship between current, magnetic field, and force, but also reinforces how we can use experimental data to calculate physical constants, verify theoretical predictions, and understand the practical applications of electromagnetism.
For this experiment, we will need the following materials and equipment. We have the main unit with the current loop, which will carry the electrical current through the magnetic field. We'll use a magnet assembly with its holder to create the magnetic field. We'll need a lab stand and rod, no more than 3/8 of an inch in diameter, to mount the main unit securely. We'll also need a digital balance that can measure to at least 0.01 grams, since the magnetic force will appear as a change in the mass reading. To power the circuit, we'll use a DC power supply and connecting cables. We'll use a ruler or caliper to measure the length of the foil section of the current loop that sits in the magnetic field. Finally, we'll use a computer with Capstone software for manual data entry, graphing, and linear fitting during the data analysis. First, we're going to set up the equipment. We mount the main unit on the lab stand and make sure it's stable. Next, we select a current loop and measure the length of the foil section that passes through the magnetic field. We record that length as L. Then we place the magnet assembly on the balance and zero it out so we start with no current. We position the stand so the foil passes directly between the magnet poles without touching them. Once the setup is aligned, we connect the power supply to the main unit, keeping the current knob at 0 to begin with. We measure and record the mass of the magnet assembly when no current is flowing. That's our baseline mass. Next, we set the current to -5 amps and record the new mass reading. We decrease the current by 1 amp each time from -phi A up to 0A and write down each mass value in table I. Then we reverse the cables to switch the direction of the current and increase it from +1 amp up to +5 amps, again recording the mass each time. After collecting all the data, we convert the change in mass to force by multiplying each mass difference by 9.81 meters per second squared. That gives us the magnetic force at each current. Next, we open Capstone and choose Manual Entry. We rename the X column as Current, A, and the Y column as Magnetic Force, N. Then we enter all our data points. Capstone automatically plots the graph. We highlight all the data and apply a linear fit. From the slope of that line, we calculate the magnetic field using the formula B equals slope divided by L. Finally, we choose another circuit, measure its new length, and use the B value we found to predict the theoretical force for a chosen current. We test that prediction experimentally and calculate the percent error to check how accurate our results are.
Hello, my name is Said Gregorio Canton, and today I will go over the data analysis for lab number 7, which covers magnetic fields and currents. A little bit of background before we go over the data analysis. We're going to be comparing two forms of the same equation, which is the force equation, the force created by the magnetic field. As we can see, this is the vector form of the theoretical equation for the force created by a magnetic field. We have current, we have the length of the wire across the magnetic field over here. This is in vector form, and in this project, we have to set it up such that the magnet is perpendicular to the scale. That means that the force that is going to be exerted is also going to be perpendicular to the scale, and therefore a sine component that would be over here in the scalar form of this equation would just equal to 1, as the angle between the scale and the vector force would be 90. This also takes into consideration the experimental form of this equation, that is basically just the change of mass as measured by the scale multiplied by the acceleration due to gravity, just good old Newton's second law. Here is our data collection for this first table. As you can see, we start with -5 amp current and go all the way up to 5 amp. The initial mass, as previously discussed, it was basically this one, the one that has 0 current, 0.1616 kilograms. This is a mass that the magnet displays as there is no current flowing through it. We have to calculate a new mass that is given when the current is active and subtract it from the original mass. This gives us a change in mass that we later use multiplying it with gravity to get a force. The linear relationship between force and current can be observed over here. This is just a normal linear equation with slope as m, y as the dependent, x as the independent variable, and just b over here. B in this case should be equal to 0, as it is the force of the current when it is equal to 0, which in this case should be 0. Y should be the force of the magnetic field. The slope should be the length and magnetic field multiplied. The independent factor should be current. Here we have the plotted graph. As you can see, table 1 is right here, going from 5 amps all the way, -5 amps all the way to 5 amps, and here is a force. We see a roughly linear trend in this graph, and it gives us a slope of 0.00156. This slope, as previously discussed, is nothing but the product of the length of the wire times the magnetic field. We can thus obtain the magnetic field by simply getting the slope and dividing it by the length of the wire, something that we can simply measure. Exactly what we do in table number 3, where to get the magnetic field equation, we simply divide the previously obtained slope by the length of the wire used, which, after calculating, we saw that it was just simply 4 centimeters long. This gives us this equation over here, which in turn gives us this value for magnetic field, 0.039. To finish off this lab, we compare the theoretical force of the magnetic field versus the experimental one. We got another setup in which we used, yet again, 5 amp current, but this time we used another wire length, which ended up just being 1 centimeter, as you can see. Right here, 0.01 meter. To calculate the theoretical, we simply use the previously obtained value of 0.039 for the magnetic field, the current, the wire length, and it gives us a total of 0.00195 newtons. Then, when having the current run through the wire, we obtain a slight change of mass, which gives us 2.25 times 10 to the power of -4 kilograms. With that value, we can calculate the experimental force from the magnetic field, which is just a change in mass times gravity, which in turn gives us the experimental force of the magnetic field, 0.00220.725 newtons. Everything, length of wire, magnetic field, current, and we obtain a 13.19% error. This error is most definitely due to the manual reading of the mass, since we have to adjust the weights to get an accurate reading of the mass in the scale. That could be attributed to the whole percent error right here, but it does come pretty close to our theoretical value. That would be everything for today. Thank you so much for watching.
In this lab, we investigate the relationship between the magnetic forces acting on a current carrying the wire and the variables that affect it. The current I, the length of the wire L, and the magnetic field strength B, and the angle theta between the current and magnetic field. Using the equation F equals I times L times B times sine theta, and keeping the angle constant at 90 degrees, we are able to analyze how changes in current directly affect the magnetic forces of the wire. By measuring the changes in apparent mass of the magnet assembly as current varied, we determined the corresponding magnetic forces values and plotted them to find a linear relationship between current and force. From the slope of this graph, we calculated the magnitude of the magnetic field produced by our magnet. Our result supported the expected linear relationship, as the current increased and the magnetic force increased proportionally, confirming the theoretical prediction. The percent error between our experimental and theoretical values was approximately 13.19% error, which shows our results were fairly accurate overall, while aiming for less than 15%. The small discrepancies likely came from the reading errors on the manual balance, since it can be difficult to judge tiny changes in mass by eye. Vibrations or movement in the setup could also have affected the balance reading slightly as the current changed. In addition, slight misalignment between the wire and the magnetic poles may have caused the magnetic field to act at less than a perfect 90-degree angle. These factors together likely contributed to the percent error we observed. Overall, this experiment clearly demonstrated the magnetic force on a current carrying the wire increases linearly with current strength and depends directly on the magnetic field intensity. It also emphasizes the importance of maintaining a stable setup and minimizing small measurement errors to improve precision in future trials.
Credits: Introduction, Geomaterials and Procedures, Pedro Data Analysis, Seath Conclusion, Aaron.